Section 5. As we have already seen, purely statical considerations also lead to the proposition of the parallelogram of forces. In special cases, in fact, the principle admits of being very easily verified. We recognize at once, for instance, that any number whatsoever of equal forces acting either by pull or pressure in the same plane at a point, around which their successive lines make equal angles, are in equilibrium. If, for example, as shown in figure 32, the three equal forces OA, OB, OC act on the point O at angles of 120 degrees, each two of the forces holds the third in equilibrium. We see immediately that the resultant of OA and OB is equal and opposite to OC. It is represented by OD and is at the same time the diagonal of the parallelogram OADB, which readily follows from the fact that the radius of a circle is also the side of the hexagon included by it. Section 6. If the concurrent forces act in the same or in opposite directions, the resultant is equal to the sum or the difference of the components. We recognize both cases without any difficulty as particular cases of the principle of the parallelogram of forces. If in the two drawings of figure 33 we imagine the angle AOB to be gradually reduced to the value 0 degrees, and the angle A'O''B' increased to the value 180 degrees, we shall perceive that OC passes into OA plus AC, which is OA plus OB, and O'C' into O'A' minus A'C', which is O'A' minus O'B'. The principle of the parallelogram of forces includes, accordingly, propositions which are generally made to precede it as independent theorems. Section 7. The principle of the parallelogram of forces, in the form in which it was set forth by Newton and Varignon, clearly discloses itself as a proposition derived from experience. A point acted on by two forces describes with accelerations proportional to the forces two mutually independent motions. On this fact, the parallelogram construction is based. Daniel Bernoulli, however, was of opinion that the proposition of the parallelogram of forces was a geometrical truth, independent of physical experience, and he attempted to furnish for it a geometrical demonstration, the chief features of which we shall here take into consideration, as the Bernoullian view has not, even at the present day, entirely disappeared. If two equal forces at right angles to each other act on a point, there can be no doubt, according to Bernoulli, that the line of bisection of the angle, conformably to the principle of symmetry, is the direction of the resultant r. To determine geometrically also the magnitude of the resultant, each of the forces P is decomposed into two equal forces Q, parallel and perpendicular to r. The relation in respect of magnitude thus produced between P and Q is consequently the same as that between r and P. We have accordingly P equals mu times Q, and r equals mu times P, whence r equals mu squared times Q. Since, however, the forces Q acting at right angles to r destroy each other, while those parallel to r constitute the resultant, it further follows that r equals 2Q. Hence, mu equals the square root of 2, and r equals the square root of 2 times P. The resultant, therefore, is represented also in respect of magnitude by the diagonal of the square constructed on P as side. Similarly, the magnitude may be determined of the resultant of unequal rectangular components. Here, however, nothing is known beforehand concerning the direction of the resultant r. If we decompose the components P and Q, as in figure 35, parallel and perpendicular to the yet undetermined direction r, into the forces U, S, and V, T, the new forces will form with the components P and Q the same angles that P and Q form with r. From which fact, the following relations in respect magnitude are determined. R over P equals P over U, and R over Q equals Q over V, R over Q equals P over S, and R over P equals Q over T, from which two latter equations follows S equals T equals PQ over R. On the other hand, however, R equals U plus V equals P squared over R plus Q squared over R, or R squared equals P squared plus Q squared. The diagonal of the rectangle constructed on P and Q represents accordingly the magnitude of the resultant. Therefore, for all rhombs, the direction of the resultant is determined. For all rectangles, the magnitude, and for squares, both magnitude and direction. Bernoulli then solves the problem of substituting for two equal forces acting at one given angle, other equal, equivalent forces acting at a different angle, and finally arrives by circumstantial considerations, not wholly exempt from mathematical objections, but amended later by Poisson, at the general principle. Section 8. Let us now examine the physical aspect of this question. As a proposition derived from experience, the principle of the parallelogram of forces was already known to Bernoulli. What Bernoulli really does, therefore, is to simulate towards himself a complete ignorance of the proposition and then attempt to philosophize it abstractly out of the fewest possible assumptions. Such work is by no means devoid of meaning and purpose. On the contrary, we discover by such procedures how few and how imperceptible the experiences are that suffice to supply a principle. Only we must not deceive ourselves as Bernoulli did. We must keep before our minds all the assumptions and should overlook no experience which we involuntarily employ. What are the assumptions, then, contained in Bernoulli's deduction? Section 9. Statics, primarily, is acquainted with force only as a pull or a pressure, that from whatever source it may come always admits of being replaced by the pull or the pressure of a weight. All forces thus may be regarded as quantities of the same kind and be measured by weights. Experience further instructs us that the particular factor of a force which is determinative of equilibrium or determinative of motion is contained not only in the magnitude of the force, but also in its direction, which is made known by the direction of the resulting motion, by the direction of a stretched cord, or in some like manner. We may ascribe magnitude indeed to other things given in physical experience, such as temperature or potential function, but not direction. The fact that both magnitude and direction are determinative in the efficiency of a force impressed on a point is an important thought, though it may be an unobtrusive experience. Granting then that the magnitude and direction of forces impressed on a point alone are decisive, it will be perceived that two equal and opposite forces, as they cannot uniquely and precisely determine any motion, are in equilibrium. So also, at right angles to its direction, a force P is unable uniquely to determine a motional effect. But if a force P is inclined at an angle to another direction SS prime, as in figure 36, it is able to determine a motion in that direction. Yet experience alone can inform us that the motion is determined in the direction of S prime and not in that of S. That is to say, in the direction of the side of the acute angle or in the direction of the projection of P on S prime. Now, this latter experience is made use of by Bernoulli at the very start. The sense, namely, of the direction resultant of two equal forces acting at right angles to one another, is obtainable only on the ground of this experience. From the principle of symmetry follows only that the resultant falls in the plane of the forces and coincides with the line of bisection of the angle, not, however, that it falls in the acute angle. But if we surrender this latter determination, our whole proof is exploded before it has begun. Section 10. If now we have reached the conviction that our knowledge of the effect of the direction of a force is solely obtainable from experience, still less then shall we believe it in our power to ascertain by any other way the form of this effect. It is utterly out of our power to divine that a force P acts in a direction S that makes with its own direction the angle alpha exactly as a force P cosine alpha in the direction S, a statement equivalent to the proposition of the parallelogram of forces. Nor was it in Bernoulli's power to do this. Nevertheless, he makes use, scarcely perceptible it is true, of experiences that involve by implication this very mathematical fact. A person already familiar with the composition and resolution of forces is well aware that several forces acting at a point are, as regards their effect, replaceable in every respect and in every direction by a single force. This knowledge in Bernoulli's mode of proof is expressed in the fact that the forces P and Q are regarded as absolutely qualified to replace in all respects the forces S, U, and T, V, as well in the direction of R as in every other direction. Similarly, R is regarded as the equivalent of P and Q. It is further assumed as wholly indifferent whether we estimate S, U, T, V first in the directions of P and Q, and then P and Q in the direction of R, or S, U, T, V, be estimated directly and from the outset in the direction of R. But this is something that a person can only know who has antecedently acquired a very extensive experience concerning the composition and resolution of forces. We reach most simply the knowledge that we have referred to by starting from the knowledge of another fact, namely that a force P acts in a direction making with its own an angle alpha with an effect equivalent to P cosine alpha, As a fact, this is the way the knowledge of the truth was reached. If, then, several forces p prime, p double prime are applied to one and the same point at the angles alpha, alpha prime, alpha double prime, with a given direction x, these forces, let us suppose, are replaceable by a single force capital pi, which makes with x the angle mu. By the familiar principle, we then have the sum of p cosine alpha equals pi cosine mu. If pi is still to remain the substitute of this system of forces, whatever direction x may take on the system being turned through any angle delta, we shall further have the sum of p cosine of alpha plus delta equals pi cosine of mu plus delta. Or the sum of p cosine alpha minus pi cosine mu times cosine delta minus the sum of p sine alpha minus pi sine mu times sine delta equals 0. If we put the sum of p cosine alpha minus pi cosine mu equal to a, and the negative of the sum of p sine alpha minus pi sine mu equal to b, then tangent r equals b over a. It follows that a cosine delta plus b sine delta equals the square root of a squared plus b squared sine of delta plus r equal to 0, which equation can subsist for every delta only on the condition that e equals the sum of cosine alpha minus pi cosine mu equals 0, and b equals the sum of p sine alpha minus pi sine mu equals 0. Whence results that pi cosine mu equals the sum of p cosine alpha and pi sine mu equals the sum of p sine alpha. From these equations follow for pi and mu the determinate values. Pi equals the square root of the sum of p sine alpha squared plus the sum of p cosine alpha squared, and tangent mu equals the sum of p sine alpha divided by the sum of p cosine alpha. Granting, therefore, that the effect of a force in every direction can be measured by its projection on that direction, then truly every system of forces acting at a point is replaceable by a single force, determinate in magnitude and direction. This reasoning does not hold, however, if we put in the place of cosine alpha any general function of an angle, phi of alpha. Yet if this be done, and we still regard the resultant as determinate, we shall obtain for phi of alpha, as may be seen, for example, from Poisson's deduction, the form cosine alpha. The experience that several forces acting at a point are always in every respect replaceable by a single force is therefore mathematically equivalent to the principle of the parallelogram of forces, or to the principle of projection. The principle of the parallelogram or of projection is, however, much easier reached by observation than the more general experience above mentioned by statical observations. And as a fact, the principle of the parallelogram was reached earlier. It would require indeed an almost superhuman power of perception to deduce mathematically, without the guidance of any further knowledge of the actual conditions of the question, the principle of the parallelogram from the general principle of the equivalence of several forces to a single force. We criticize accordingly in the deduction of Bernoulli that which is easier to observe is derived from that which is more difficult to observe, which is a violation of the economy of science. Bernoulli deceives himself in thinking that he does not proceed from the easier to the more difficult. Let us further remark that the fact that the forces replace one another, which is involved in the principle of the parallelogram, is already contained in another, the principle of the composition of motions. As we have to do with uniform or symmetrical systems of forces, all equal in magnitude, each can be affected by the others, even if they are not independent, only to the same extent and in the same way. Given but three forces, however, of which two are symmetrical to the third, and even then the reasoning, provided we admit that the forces may not be independent, presents considerable difficulties. Section 11. Once we have been led, directly or indirectly, to the principle of the parallelogram of forces, once we have perceived it, the principle is just as much an acquisition as any other. If the observation is recent, it is of course not accepted with the same confidence as old and frequently verified observations. We then seek to support the new observation by the old to demonstrate their agreement. By and by, the new observation acquires equal standing with the old. It is then no longer necessary constantly to reduce it to the latter. Deduction of this character is expedient only in cases in which observations that are difficult directly to obtain can be reduced to simpler ones more easily obtained, as is done with the principle of the parallelogram of forces in dynamics. Section 12. The proposition of the parallelogram of forces has also been illustrated by experiments especially instituted for the purpose. An apparatus very well adapted to this end was contrived by Cauchy. The center of a horizontal divided circle, as shown in figure 37, is marked by a pin. Three threads F, F prime, F double prime, tied together at a point, are passed over grooved wheels R, R prime, R double prime, which can be fixed at any point in the circumference of the circle, and are loaded by the weights P, P, P prime, P double prime. If three equal weights be attached, for instance, and the wheels placed at the marks of division 0, 120, and 240, the point at which the strings are knotted will assume a position just above the center of the circle. Three equal forces acting at angles of 120 degrees, accordingly, are in equilibrium. If we wish to represent another and different case, we may proceed as follows. We imagine any two forces P and Q acting at any angle alpha, represent them by lines, and construct on them as sides a parallelogram. We supply further a force equal and opposite to the resultant R. The three forces P, Q, and negative R hold each other in equilibrium at the angles visible from the construction. We now place the wheels of the divided circle on the points of division 0, alpha, and alpha plus beta, and load the appropriate strings with the weights P, Q, and R. The point at which the strings are knotted will come to a position exactly above the middle point of the circle. Section 4. The Principle of Virtual Velocities, Part 1. We now pass to the discussion of the principle of virtual or possible displacements. The truth of this principle was first remarked by Stevinus at the close of the 16th century in his investigations on the equilibrium of pulleys and combinations of pulleys. Stevinus treats combinations of pulleys in the same way they are treated at the present day. In the case A, figure 39, equilibrium obtains when an equal weight P is suspended at each side for reasons already familiar. In B, the weight P is suspended by two parallel cords, each of which accordingly supports the weight P over 2, with which weight, in the case of equilibrium, the free end of the cord must also be loaded. In C, P is suspended by 6 cords, and the weighting of the free extremity with P over 6 will accordingly produce equilibrium. In D, the so-called Archimedean or potential pulley, P in the first instance is suspended by 2 cords, each of which supports P over 2. One of these 2 cords in turn is suspended by 2 others, and so on to the end, so that the free extremity will be held in equilibrium by the weight P over 8. If we impart to these assemblages of pulleys displacements corresponding to a descent of the weight P through the distance h, we shall observe that as a result of the arrangement of the cords, the counterweight P in A will ascend a distance h, in B will ascend a distance 2h, in C 6h, in D 8h. In a system of pulleys in equilibrium, therefore, the products of the weights into the displacements they sustain are respectively equal. Stevinus in Latin puts it thus: ut spatium agentis ad spatium patientis, sic potentia patientis ad potentiam agentis. In this remark is contained the germ of the principle of virtual displacements. Section 2. Galileo recognized the truth of the principle in another case, and that a somewhat more general one, namely in its application to the inclined plane. On an inclined plane, figure 40, the length of which AB is double the height BC, a load Q placed on AB is held in equilibrium by the load P acting along the height BC if P equals Q over 2. If the machine be set in motion, P equals Q over 2 will descend, say the vertical distance h, and Q will ascend the same distance h along the incline AB. Galileo, now allowing the phenomenon to exercise its full effect on his mind, perceives that equilibrium is determined not by the weights alone, but also by their possible approach to and recession from the center of the earth. Thus, while Q over 2 descends along the vertical height, the distance h, Q ascends h along the inclined length, vertically, however, only h over 2. The result being that the products QH over 2 and Q over 2 times h come out equal on both sides. The elucidation that Galileo's observation affords and the light it diffuses can hardly be emphasized strongly enough. The observation is so natural and unforced, moreover, that we admit it with instinctive acceptance. A machine in which an equality of displacement takes place only on one side, while bodies when on the whole no heavy mass can descend, such a fact appears instinctively acceptable. Galileo's conception of the inclined plane strikes us as much less ingenious than that of Stevinus, but we recognize it as more natural and more profound. It is in this fact that Galileo discloses such scientific greatness, that he had the intellectual audacity to see in a subject long before investigated more than his predecessors had seen, and to trust to his own perceptions. With the frankness that was characteristic of him, he unreservedly places before the reader his own view, together with the considerations that led him to it. Section 3. Torricelli, by the employment of the notion of the center of gravity, has put Galileo's principle in a form in which it appeals still more to our instincts, but in which it is also incidentally applied by Galileo himself. According to Torricelli, equilibrium exists in a machine when, on a displacement being imparted to it, the center of gravity of the weights attached thereto cannot descend. On the supposition of a displacement in the inclined plane last dealt with, P, let us say, descends the distance h, in compensation whereof q vertically ascends h sine alpha. Assuming that the center of gravity does not descend, we shall have ph minus qh sine alpha over p plus q equals 0, or ph equals qh sine alpha, and hence p equals q sine alpha equals q times bc over ab. If the weights bear to one another some different proportion, then the center of gravity can descend when a displacement is made, and equilibrium will not obtain. We expect the state of equilibrium instinctively when the center of gravity of a system of heavy bodies cannot descend. The Torricellian form of expression, however, contains in no respect more than the Galilean. Section 4. As with systems of pulleys and with the inclined plane, so also the validity of the principle of virtual displacements is easily demonstrable for the other machines, for the lever, the wheel and axle, and the rest. In a wheel and axle, for instance, with the radii r and r and the respective weights p and q, equilibrium exists, as we know, when pr equals qr. If we turn the wheel and axle through the angle alpha, p will descend r alpha, and q will ascend r alpha. According to the conception of Stevinus and Galileo, when equilibrium exists, pr alpha equals qr alpha, which equation expresses the same thing as the preceding one. Section 5. When we compare a system of heavy bodies in which motion is taking place with a similar system which is in equilibrium, the question forces itself upon us: what constitutes the difference of the two cases? What is the factor operative here that determines motion, the factor that disturbs equilibrium, the factor that is present in the one case and absent in the other? Having put this question to himself, Galileo discovers that not only the weights but also the distances of their vertical descents, the amounts of their vertical displacements, are the factors that determine motion. Let us call P, P prime, P double prime, the weights of a system of heavy bodies, and H, H prime, H double prime, their respective simultaneously possible vertical displacements, where displacements downwards are reckoned as positive and displacements upwards as negative. Galileo finds then that the criterion or test of the state of equilibrium is contained in the fulfillment of the condition pH plus P prime H prime plus P double prime H double prime, and so on, equal to 0. The sum pH plus P prime H prime, and so forth, is the factor that destroys equilibrium, the factor that determines motion. Owing to its importance, this sum has in recent times been characterized by the special designation work. Section 6. Whereas the earlier investigators, in the comparison of cases of equilibrium and cases of motion, directed their attention to the weights and their distances from the axis of rotation, and recognized the statical moments as the decisive factors involved, Galileo fixes his attention on the weights and their distances of descent, and discerns work as the decisive factor involved. It cannot, of course, be prescribed to the inquirer what mark or criterion of the condition of equilibrium he shall take account of when several are present to choose from. The result alone can determine whether his choice is the right one. But if we cannot, for reasons already stated, regard the significance of the statical moments as given independently of experience as something self-evident, no more can we entertain this view with respect to the import of work. Pascal errs, and many modern inquirers share this error with him when he says, on the occasion of applying the principle of virtual displacements to fluids, it is clear that it is the same thing to raise 1 inch 100 pounds of water as to raise 100 inches 1 pound of water. This is correct only on the supposition that we have already come to recognize work as the decisive factor, and that it is so is a fact which experience alone can disclose. If we have an equal-armed, equally weighted liver before us, we recognize the equilibrium of the liver as one that of itself is uniquely determined, whether we regard the weights and the distances or the weights and their vertical displacements as the conditions that determine equilibrium. Experimental knowledge of this or a similar character must, however, in the necessity of the case, precede any judgment of ours with regard to the phenomenon in question. The particular way in which the disturbance of equilibrium depends on the conditions mentioned, that is to say, the significance of the statical moment PL or of the work PH, is even less capable of being philosophically excogitated than the general fact of the dependence. Section 7. When two equal weights with equal and opposite possible displacements are opposed to each other, we recognize at once the subsistence of equilibrium. We might now be tempted to reduce the more general case of the weights P and P prime with the capacities of displacement H and H prime, where pH equals P prime H prime, to the simpler case. Suppose we have, for example, figure 41, the weights 3P and 4P on a wheel and axle with the radii 4 and 3. We divide the weights into equal portions of the definite magnitude P, which we designate by A, B, C, D, E, F, G. We then transport A, B, C to the level +3 and D, E, F, G to the level -3. The weights will, of themselves, neither enter on this displacement, nor will they resist it. We then take simultaneously the weight G at the level 0 and the weight A at the level +3, push the first upwards to -1 and the second downwards to +4. Then again, and in the same way, F to -2 and B to +4, E to -3, and C to +4. On all these displacements, the weights offer no resistance, nor do they produce them of themselves. Ultimately, then, A, B, C, or 3P appear at the level +4, and D, E, F, G, or 4P at the level -3. Consequently, with respect also to the last mentioned total displacement, the weights neither produce it of themselves, nor do they resist it. That is to say, given the ratio of displacement here specified, and the weights will be in equilibrium. The equation 4 times 3p minus 3 times 4p equals 0 is, therefore, characteristic of equilibrium in the case assumed. The generalization pH minus p prime h prime equals 0 is obvious. If we carefully examine the reasoning of this case, we shall quite readily perceive that the inference involved cannot be drawn unless we take for granted that the order of the operations performed and the path by which the transferences are effected are indifferent. That is, unless we have previously discerned that work is determinative. We should commit, if we accepted this inference, the same error that Archimedes committed in his deduction of the law of the lever, as has been set forth at length in a preceding section, and need not in the present case be so exhaustively discussed. Nevertheless, the reasoning we have presented is useful in the respect that it brings palpably home to the mind the relationship of the simple and the complicated cases. The universal applicability of the principle of virtual displacements to all cases of equilibrium was perceived by John Bernoulli, who communicated his discovery to Varignon in a letter written in the year 1717. We are now in a position to formulate the principle in its most general form. At the points A, B, C, and so forth, figure 42, the forces P, P prime, P double prime act. Impart to the points any infinitely small displacements Z, Z prime, Z's double prime, compatible with the conditions of the connections of the system. Then the sum of the projections PZ plus P prime, Z prime, plus P double prime, Z double prime, and so on, is equal to 0. We consider these displacements on the directions of the forces. These projections we consider positive when they fall in the direction of the force, and negative when they fall in the opposite direction. The products PZ, P prime, Z prime, P double prime, Z double prime are called virtual moments, and in the two cases just mentioned have contrary signs. Now the principle asserts that for the case of equilibrium PZ plus P prime, Z prime plus P double prime, Z double prime, and so on, or more briefly, the sum of pz equals 0. Section 9. Let us now examine a few points more in detail. Previous to Newton, a force was almost universally conceived simply as the pull or the pressure of a heavy body. The mechanical researches of this period dealt almost exclusively with heavy bodies. When now, in the Newtonian epoch, the generalization of the idea of force was effected, all mechanical principles known to be applicable to heavy bodies could be transferred at once to any forces whatsoever. It was possible to replace every force by the pull of a heavy body on a string. In this sense, we may also apply the principle of virtual displacements, at first discovered only for heavy bodies, to any forces whatsoever. Virtual displacements are displacements consistent with the character of the connections of a system and of one another. If, for example, the 2 points of a system, A and B, at which forces act, are connected by a rectangularly bent lever free to revolve about C, as in figure 43, then all virtual displacements of B and A are elements of the arcs of circles having C as center. The displacements of B are always double the displacements of A, and both are in every case at right angles to each other. If the points A and B are connected by a thread of the length L, adjusted to slip through stationary rings at C and D, then all those displacements of A and B are virtual, in which the points referred to move upon or within two spherical surfaces described with the radii R1 and R2, about C and D as centers, where R1 plus R2 plus CD equals L. The use of infinitely small displacements instead of finite displacements, such as Galileo assumed, is justified by the following consideration. If two weights are in equilibrium on an inclined plane, figure 44, the equilibrium will not be disturbed if the inclined plane, at points at which it is not in immediate contact with the bodies considered, passes into a surface of a different form. The essential condition is, therefore, the momentary possibility of displacement in the momentary configuration of the system. To judge of equilibrium, we must assume displacements vanishingly small and such only, as otherwise the system might be carried over into an entirely different adjacent configuration, for which perhaps equilibrium would not exist. That these displacements themselves are not decisive, but only the extent to which they occur in the directions of the forces, that is, only their projections on the lines of the forces, was, in the case of the inclined plane, perceived clearly enough by Galileo himself. With respect to the expression of the principle, it will be observed that no problem whatever is presented if all the material points of the system on which forces act are independent of each other. Each point thus conditioned can be in equilibrium only in the event that it is not movable in the direction in which the force acts. The virtual moment of each such point vanishes separately. If some of the points be independent of each other, while others in their displacements are dependent on each other, the remark just made holds good for the former, and for the latter, the fundamental proposition discovered by Galileo holds that the sum of their virtual moments is equal to 0. Hence, the sum total of the virtual moments of all jointly is equal to 0.